today with Mr. Hausken. We'll be really focusing on quantum photonics. So as a senior industry advisor at the Optical Society of America, he's been developing this roadmap. And so we will first let him present this roadmap. This will take somewhere between 30 and 40 minutes. You may ask questions. Donc, si vous avez des questions, vous pouvez les envoyer par écrit. Donc, vous avez en bas de votre fenêtre dans l'application Zoom un petit logo. Si vous avez la version française comme moi, c'est Q et R, questions et réponses. So you have a logo at the bottom of your screen, Q&A. You can type in your questions. We will accumulate the questions. You can type in at any time. We'll accumulate the questions during the talk. And then at the end, we'll have some time for questions and also discussions if there's any other points that you want to cover. So with this said, I will cede the floor to Mr. Tom Hausken. Welcome.
Merci. Merci bien pour l'opportunité à présenter aujourd'hui. And I'll stop there with my French because I'll certainly get into trouble and say something wrong. So yes, I'm Tom Hausken. I'm Senior Industry Advisor at OSA and OSA Industry Development Associates, which is OIDA, the trade association that OSA operates. Corporate membership organization that we have. So the way that I'll do this is I'm going to spend most of the time talking about the quantum roadmap that we published earlier this year. So it went to members at first in March, and then to non-members. It's been available since June. You can download it, and I'll show you information on that later. So this is a quantum roadmap specifically for photonics. And then at the end, I have a few minutes to talk about Canada and trends. Now that could easily be the full 40 minutes, full hour, but we'll confine it to just a few minutes. And if you want to discuss it in the Q&A afterwards, we can do that too. And maybe I can come back sometime and talk about those. So let me go ahead and share the screen, and let's get on with the part about the photonics roadmap. And I believe the screen is sharing. Is that right, Nicolas? Okay.
That's
so. Yeah, so first, most of the talk will talk about this quantum roadmap that we published, and it was supported by Corning Incorporated, which we very much appreciate. I want to give a shout out to Corning. And also we worked with a company called INTRIQ Corporation, which is a consulting organization, did a lot of the research and writing of the document. We did the oversight, but we have to give them a lot of credit for some really good work that they did. Okay. Now, Quantum 2.0 is not in the title. It's not really discussed in the report, but it comes up. OSA just supported a conference last week called Quantum 2.0 Conference. And so since this can be kind of a more general talk here, I just wanted to address this. So I can't speak for the conference that we just supported, but what defines Quantum 2.0? Because I think it helps to understand maybe a lot of what goes into our report. Does it mean textbook quantum properties? We've been using quantum effects in the past, so what's different now? Now we can eliminate broadening. So that's there's that. Does it require entanglement? Is that the part that's different? Or is it just new and improved? And I would say, for the most part, it's the new and improved part. We're not trying to restrict things. It's a broad community out there, and so we're not trying to define narrowly what it means. So you can use that going forward, even though it's not really part of the report. Okay, there are a number of different efforts out there. And so one thing that we want to talk about is how does our roadmap fit into that? So first of all, this is a map of quantum computing efforts as reported by a Quantum Computing Report a couple of years ago. So there's certainly more efforts out there than are shown on this chart. And there's also efforts in quantum sensing and quantum communications and even, the basic science of quantum. So just to give you the idea of the scope of how much is going on. Well, there's a number of reports as well that have the word roadmap in it. Some may look a little bit like a research review, maybe forward-looking, but not necessarily giving you any perspective about what's likely to happen or what it means for the photonics specifically. Some other reports start to look like government planning documents, strategic plans for funding quantum initiatives. And so those are directed specifically for those national government spending programs. Our document is intended to be a technology roadmap, not a market forecast, not even a technology forecast, really, but looking at quantum photonics, specifically the optical components and the specifications that will be needed to enable that, maybe some gaps in the technology. Now, it's very early to do that. To do a technology roadmap, you really want to pick an application, and there's a great many applications, too many to choose from. Also, it's very early, so you can't really pick winners and losers in some of these technologies. So it's really more of a proto roadmap at this point. And then later, maybe through conversations, we can improve on it, extend it, what have you. So it's an early roadmap 1.0. So for many of you may already be familiar with the quantum applications out there, but just to give you an idea, this shows 3 major columns: quantum sensing and timing, quantum communications, and quantum computing. 3 major applications areas, and you'll see that come up later. Along the rows are 5 big end markets: telecom, medicine, oil and gas, and so on. And you can add more if you want. And then some examples in each cell there of how you would use these different quantum technologies in applications for those end markets. Now, this is not meant to be exhaustive. The idea is just that there are a lot of applications. If you're not familiar with it, this gives you a little bit of an idea of all the different things that it can be used in. Now, to take a 70-page roadmap document and summarize it in one chart is pretty ambitious. But if you were to try to do it, this chart would do it. So what you have here is, on the left-hand side, those 3 main application areas that I just mentioned: quantum sensing, quantum communications, and quantum computing. And then going along towards the right side of the screen, you have is time. You're moving in time. So there's gravimeters and large format atomic clocks that are arguably commercial today. In fact, in some cases, have been commercial for quite some time. But we want to make them smaller, more robust, lower cost, so that we can have miniaturized sensors that can go out more commercially. Quantum communications also, you could buy the equipment and put together a system today, but there is missing a quantum memory and quantum repeater. Also, we need to increase the distance and the key rate, or the data rate, as the case may be, for quantum networking. And by the way, quantum networking isn't addressed that much in the document, but that is something that will be needed to scale up quantum computing. You may have some quantum computing in a dilution refrigerator, but then to make a bigger computer, you're going to need to connect them together. And that's where the quantum networking comes in. And then quantum computing at the bottom. Yes, there are systems you can buy today, D-Wave, for example, but what the community is looking for is a fault-tolerant quantum computer that can do some really interesting algorithms. And you've probably heard about that in the media. So just to go very quickly over some of these applications, the quantum sensors, a big area. On the left-hand side, you see a quantum accelerator. In the center, a quantum magnetometer. On the right-hand side, a quantum differential gravimeter. And you'll notice that these are big. Looks like they take a couple PhDs to fine-tune. They look a little bit delicate. And so the idea, as you can imagine, is to try to shrink these, make them more robust, make them lower cost and all that. So they do exist, and there are even some that are commercial, but that's the idea. So just to give you an example, in atomic clocks, microwave clocks or atomic clocks have existed for many decades, but optical clocks have appeared in the last few decades and are now the more precise standard, and again, there are commercial products out there, and they continue to advance every year. So that's the state of where things are at this point. Okay, so quantum sensors, they are commercial or near commercial in some cases, atomic clocks particularly, gravimeters as well. Looking forward, there could be GPS-free navigation using these tools, medical imaging. Notice I haven't included quantum LiDAR here. There's a number of other applications that people are talking about. But let me move on to quantum communications. Now, you may have heard about the satellite that China launched, the Messias satellite, back in 2016, and they've done a number of experiments with it, including this one where they exchange keys between Beijing and Austria and back. And they've also demonstrated on land over 1,000-mile link hopping a number of trusted nodes, where the short links are using quantum key distribution, but then they go through a trusted node and then they pass it on again. And so that's been demonstrated, and you can buy equipment today and install that. It's very early stage, but it's at that level of demonstration. Now, this chart here gets a little bit into a little bit of a controversial area. So the whole logic for quantum key distribution kind of rests on quantum computing. It doesn't have to, but it sometimes you'll hear it presented that way. So will a quantum computer exist that can factor classic asymmetric public key ciphers? In other words, will a quantum computer come along, which we'll talk about in a moment, that could upset our entire encryption system? And if not, then maybe you don't need quantum key distribution. Maybe you do. Maybe you like it as an extra tool in your toolbox, and that is an argument for it. But if that quantum computer does come along, then the next question is, will quantum resistant cryptography, also known as post-quantum cryptography, will that exist first, in making the quantum key distribution irrelevant? Then if it does, well, maybe you don't need QKD. And if it does not, then maybe it is necessary. So even if this quantum computer is developed many, many years in the future, you're continuing to encrypt documents. And plus, it takes time to roll out these new technologies. And so you need to be working on it today for that to happen. So again, you may want the tool anyway. And there are other things to do with quantum communications besides just distribution of keys. But I think this logic sort of comes up a lot with the in discussions about funding. So it is quasi-commercial today. Satellite-based QKD has been demonstrated, but it's not commercial, certainly. Quantum random number generators are commercially available. You can buy that. And meanwhile, they're working on this post-quantum cryptography in parallel with that. Now, then the chart leapfrogs to quantum internet sometime far into the future, relatively far into the future. But what's not shown here and really should be on there is the intermediate step of quantum networking and some other things that you can do in quantum communications as well, with fault detection maybe, or some things like that. And so maybe in the beginning QKD, and then after that some other applications. Now, quantum computing. This is a joke. I'll let you sort of read through it here. How's the quantum computer coming along? Great. It's both successful and not started. You know, it's a classic Schrodinger cat joke. Can I observe it? Well, that's a tricky question because you'll collapse the wave function. And if you're a quantum person, you get it. But you've probably seen these Schrodinger cat jokes, even if you're not a quantum person, and you can find them all over the internet. I think this one's actually very appropriate. It's from 2012, believe it or not. And quantum computing has come a long ways, but it is simultaneously both totally successful if you talk to D-Wave and some of the companies that are doing these early stage things, and they're very excited about the progress that they're making, relatively quick progress, considering the technical challenge, but then it's also not even started if you're one of the people that says, well, you really need to have this fault-tolerant computer. Requires a lot of qubits, and we're far from that goal, and so on. So anyway, that fairly sums up the quantum computing area here. It kind of depends which side you're on. So it gets a lot of media attention. It is the more speculative of the three. You'll see, you know, IEEE Spectrum magazine had this article a couple years ago. Google claimed a year ago quantum supremacy. Meanwhile, Honeywell, and just recently out of China, there's some rumors or leaks that maybe they achieved something really big. There's also, a year ago, there was a discussion that the word supremacy is kind of offensive. And if you go back to, I think this was Nature, and try to find this article now, you won't find, the article's there, but the title's changed. It actually appears under a different title now. Anyway, so there's a number of different approaches for this quantum computing, and you may be familiar with these, from superconducting to photonic. The photonic one is particularly interesting. They all use photonics in some way, because no matter, either you're delivering light in, or you know, laser light in to control the qubits and so forth, or if nothing else, you have to network these things from one chamber to another. And even if you're not doing it today, at some point you'll need to do that. And photons is really the only practical way to do that. And that's not easy, but that's the way to go. But the photonic approach on the very far side is very interesting, because that uses a purely photonic approach at room temperature. The detectors have to be cooled, but the computer itself is actually at room temperature. And if they can scale it up, could be really, really exciting. In any case, there's 3 companies working on it. One of them is Canadian. Now, to give you an idea of how this all fits in 2018, the spending on hyperscale data centers was a whopping $120 billion. This is money that's spent by Facebook, Microsoft, Amazon, Alibaba, et cetera, to run their data centers. The high-performance computing market is about $14 billion, but the part that's supercomputers that you think of, like the big room full of computing equipment, like a data center, but dedicated to supercomputing, that's about $5 billion. Now, the quantum mainframe people don't like to be compared to the supercomputer market. They'll say that it's not the same thing. They're not going after the same market. This is a whole different thing, which is all true. But just to give you an idea, you can certainly imagine that in the beginning, it's going to be a small-ish just to get started, $500 million. Maybe it could get up to around 5 billion or so. Who knows? For the most part, probably end users are not going to buy the quantum computer. They're going to lease the services off of it. In fact, you can go today and use IBM's quantum computer and do some programming. I did. I'm not even a quantum expert. I was able to register and get an account within probably 90 seconds and program something within 5 minutes and get an output. It didn't really make a lot of sense. It wasn't really a smart program, but you could do it. And so that's probably the future there. And the thing is, the economic impact, though, might be far, far larger than these numbers here. And by the way, keep in mind, we're only talking about quantum computing in this chart. So the economic impact could be what? Well, you might solve COVID, or you might be impactful for national security reasons. So you can imagine that companies and countries are very, very interested in this because they don't want to fall behind, even though the market for it might not be that necessarily that big. Okay, so it gets the most media exposure, but it's also the most speculative. So today you have these annealers that you can buy, and NISC type of computers, but the idea is that sometime in the future there'll be this fault-tolerant gate-based quantum computer, and you'll hear claims that it's just around the corner. In a couple of years there'll be one, but I think there's also a lot of concern in the industry that it gets overhyped, and so it's coming, it's moving along, but it'll take a little while before it's really a commercial type of product. And you'll see a lot of the things that have to go into making that happen. So this is a market forecast from Yole. There's a couple other forecasts out there, but Yole's is, I think it's pretty reasonable. You'll notice this is over 10 years, pretty long range. Sensing exists already as a market for quantum technology. This, by the way, includes everything, not just photonics. Its growth, they see it as relatively modest. In cryptography, stronger growth, and then computing is the big one. So again, it takes a long time and it gets a lot of media exposure, but it would have a big payoff relative to these other 2 technologies. Now, one thing about this is that if you look carefully, inside of Riole's numbers in 2030 is that service component. So it's not all hardware that they're talking about here. There's the component that goes into services. So again, IBM or Microsoft or whoever Honeywell may have a computer and they're going to lease it to you. And so that income is counted in this number as well. So if you take out the hardware part and then you say, okay, some part of that is optics, then the actual amount going to optics is much smaller. So the big thing driving it is FOMO, also known as fear of missing out, or downside risk management, as they call it on Wall Street. So when you hear that Wall Street is involved and they're kicking the tires, well, that's very exciting, certainly, but at the same time, Wall Street's big, and they're putting a few people on this just to make sure they don't miss the boat. Maybe somebody comes along with a quantum computer that solves some stock picking algorithm, and they want to know about that. So Google's claiming a breakthrough. It's a potential threat to American security, et cetera, et cetera. So that's that fear of missing out part. Meanwhile, there is a market, though, picks and shovels. So we call it picks and shovels because these are the tools that you use to develop the quantum technology until such time that you can sell the actual stuff. So this comes from 1849 out of the gold rush in California, in the Bay Area, actually, where people made their money on selling picks and shovels and denim jeans and so forth. And for the most part, the miners didn't. It's a high risk area, going out and mining and looking for gold. And so a few people made money, but for the most part, most of them did not. But where the money was made was on these picks and shovels. So we look at it as having two markets. The end product market is somewhere in the future, and we're very excited and hopeful for that. But in the meantime, we estimate that there's about $2 billion that goes into funding. Most of that's for salaries, but some part of that, maybe a couple $100 million, goes into cryogenic equipment and microwave cables, but even $100 million going to photonics alone. So this would be specialized lasers, single photon detectors, single photon sources, fiber, specialized fiber for visible wavelengths and things like that. So that is, it's not a lot of money, but it is nice money for the companies that are in it. These are companies like Toptica and M Squared and Aurea Technology and Menlo Systems. They can make money in this area while the R&D goes on until such time as other markets start to take off. So now, what about the roadmap itself? All of this is kind of context leading up to what the purpose of the roadmap is, which is to identify these specifications, what's actually needed. And again, I can't go into all the details just in this talk, but just to give you an idea, this shows a network of the different pieces. So there's a computing piece, there's in red is a quantum repeater representing a network and the quantum sensor. And then you have all these different components that would go in to make that happen. Single photon sources, single photon detectors, lasers, fiber and waveguides and modulators and all these different things. And they would all have different requirements, and they'd have different requirements based on the applications. So what we can do here, besides calling out a lot of these things to look for, okay, what's needed the most or what's most missing? Also, what are the common things that they are all looking for? And just to drill down a little bit further, this shows you, it's a busy slide, but the idea is that you have on the left-hand side those three categories of sensing, communications, and computing, and then within that, a number of different technologies that are used for the applications. So for example, atom interferometers are used in gravimeters and magnetometers. Nitrogen vacancy color centers are used in magnetometers. And then as you go across the screen, in green are identified those components, optical components that are required. So lasers, for example, in some cases, and then, or may be necessary in yellow. And then if it's blank, it's not necessary, not required. And so again, we can start to drill down specifically application by application, technology by technology, what's needed. Now, so generalizing across all of this is one of the main points of the roadmap. It's actually in the title. Every photon counts. And this doesn't mean just loss, but everything you can imagine. This is quantum, so every photon that you lose, it's a very expensive, high quality, high value photon. You are looking for deterministic sources, and they may be entangled, and so every single photon counts. That also applies to noise, phase noise, and wavelength, and mode hopping, and all of this. So when we say every photon counts, what it means is you're really asking for some extreme requirements on quantum. Integrated photonics is very attractive. So it can be used in a lot of different places, from sensing to computing. I mentioned that there are three companies that we know of that are working on integrated photonics specifically for computing, where the integrated photonics is actually necessary. But in other areas, it might help with reducing parts count, making it more robust, and that sort of thing. In those cases, it may not be the first place to go. It may be for the second generation products. We're not sure yet, but certainly it comes up a lot, and there's a lot of hope for integrated photonics as a solution. Swap C, lower swap C, that's size, weight, and power, and cost. So this gives you an idea. These are examples that exist today in optical clocks. So on the upper right-hand corner are these master clocks. They're huge, take up a room, all the way down to something that's very small, the size of a coin on the lower left-hand corner, and a lot lower price, also a lot lower precision. And so the idea is either make those parts that are down in the lower left-hand corner higher precision, or make the ones on the upper side of the rectangle lower cost and smaller. And so that's the idea: reduce size, weight, and power and cost, while trying to maintain performance. Another thing that you see a lot is moving from science to engineering, and or moving from the lab, you could say, to the field. So on the left-hand side, there is a quantum, well, it's cryo hardware for a Rigetti computer. Now, it contains a quantum computer on the inside, but that quantum computer is very, very small. Everything else is this different stages of the cryogenics to bring it down to millikelvin temperatures. And then next is, this is a transportable optical lattice clock. It fits into the trailer that you see in the upper right-hand corner of the photo. And then on the right-hand side is an example of some size reduction. Now, obviously not everything can be reduced down to this kind of compact size, but that's a MEMS-based optical gravimeter. And that's the idea of what can we do to try to reduce this, make it get away from cryo temperatures, get into something smaller and robust. Now, one thing I want to really point out here for those people who don't do this every day is it's not just a matter of engineering. We really want to avoid that. It's okay, they've demonstrated it in the lab, now it's just engineering. In fact, it's kind of like starting all over from the beginning. You've demonstrated in the lab, but now you have to engineer everything all over again, because all that stuff you did in the lab is no good. It's not going to sell, it's not going to be robust in the field, and all the welds and things, everything that you have to do to make something suitable for commercial, well, that has to be rethought in terms of quantum. And so it is absolutely a very big hurdle to achieve. Quantum requires many disciplines. This is an example from quantum computing specifically, but it gives you, I think, a really good idea. I think one thing that happens is we hear about a talent shortage, and you imagine quantum is really spooky, mysterious stuff. And so we need quantum physicists for sure. Well, yeah, but you also need people who are experts in electrical control. There's a lot of control going on because you have lasers all coming in at the same place, and you're trying to control these qubits. And Google actually uses a supercomputer to do its calculations for its quantum computer. So you don't eliminate the classical computer at all. You need that to prepare and then interpret the results afterwards, and just to do all the setup. So you need photonics, certainly, mechanical, thermal, cryogenics, and then you need all this software. Now, those of us who are hardware people, and especially photonics people, we tend to think that what we're doing is, the most interesting and exciting and most important stuff. And if not, at least the hardware is. But that software is really important. If nothing else, you have to have all that stuff in place for these commercial products to go out. If you don't have applications ready, if customers can't do programming, whatever, then it's no good. Of course, you can work on it along the way. And there are many efforts and companies set up now working on that in parallel. So it's a fantastic effort, going much more quickly than classical computing ever did. But you have to understand that all of that is necessary for this to work. Okay, they also have utility in non-quantum, that is classical markets. So these adjacent markets are really important. If you can invest in more than one application here where there's some kind of payoff, then it's going to make quantum go much more quickly. So for example, high efficiency, low dead time, single photon detectors are useful, yes, for QKD and quantum photonic computers, but also for low light imaging, classical, like microscopy. Low loss integrated photonics chips and high speed low loss switches would be useful, yes, in quantum, but also in classical telecom as well. So we need to look for these adjacent markets so that we can co-invest, and some investment in quantum or in the other areas can pay off in more than one way. Okay, key takeaways from the roadmap, getting to the end of this part of the talk. The key end markets, sensing and timing and communications are near-term quantum. In fact, some commercial products are already out there. Computing is longer term, but it is the more speculative market. You hear a lot more about it in the media, but it's more speculative. Market's not huge, but it's driven by FOMO, the fear of missing out, and the overall impact. So you can understand that companies like Microsoft and IBM and so on are very interested, and also nations like China and the United States are willing to spend $1 billion. It's not really that much money out of national security budgets to make sure that they're not left behind in this area. Meanwhile, R&D is a market, so about $2 billion a year is what we estimate. We're currently going back and looking at that in more detail now. But the photonics part, the picks and shovels, about $100 million a year. And that's a nice business for the companies that are in that. And they'd certainly like to see it grow. But meanwhile, as this continues to roll out, they're continuing to bring in money on that market. What it means for photonics, as I said, every photon counts. That's not just loss or efficiency, but noise, everything that you can imagine. Integrated photonics is a technology to watch. It's early, so a little bit early to pick winners and losers, but certainly there's a lot of interest in that. Swap-C, we want lower size, weight, and power, and cost. And that leads us to the point that for the most part, that photonics technology exists. But as someone said last week at our roundtables at OSA's conferences, we held 2 roundtable discussions on this. They're off the shelf, but they're on a very high shelf in the back, or another person called it academic grade products. So yes, you can use them in the lab, but they're not suitable. And so for commercial products. And so the engineering ecosystem needs development. Now, what does the ecosystem mean? If you have a small company, they can make the part for you, and they might even be able to invest to make it commercial grade for you. But that's a big risk, and they're not sure if they're picking the right technology there. And so they may not be willing to do the investment, certainly not alone. Whereas a large company does have the deep pockets, they can do that investment, but then even Google will develop some of its own stuff in-house because it can afford to, and why is it going to invest in the ecosystem for the sake of its competitors and lose control over it? So that's a problem that the industry can come to a standstill just because you have these different pieces of the ecosystem that are sort of locked up. The improvements can help classical adjacent markets and applications too. And there is a talent shortage in the quantum physicists as well, but it's really across engineers and across disciplines. And we even hear that it's really about just plain everyday engineers and technicians as well, not just quantum. So we're very active in quantum photonics. We're a member of the QEDC, which is the US Quantum Economic Development Consortium. We produced the roadmap this year. We want to continue that discussion and refine it over time. OSA was also one of the founding members of the US National Photonics Initiative, which was itself a big force behind getting the National Quantum Initiative in the US passed, which is legislation from the US government to fund $1 billion worth of photonics. And then we have these conferences. Last week we hosted the Quantum 2.0. We have roundtables. OIDA's hosting roundtable. We're going to host another one in a month at a couple weeks actually. Photonics Days, Berlin, Brandenburg. It will be in the evening in Germany, but available to watch. It's free, so you can join that and watch that roundtable discussion in a couple weeks if you like. So this is the document. Down lower in the screen, what you see is how to download it. That's for OIDA members, corporate members. It's osa.org/industry reports, and then non-members, you have to register, just put your name in, and then osa.org/OIDA roadmap. So I encourage you to go look that up and download it and take a look at it if you're interested in this topic. And I'm going to go on with the presentation, but and I'll show this slide again at the end, but just, by the way, if you have any questions about any of this, you can contact me, thoskin@osa.org, or if you have questions about OIDA and OSA, oida@osa.org. So now I'm going to go on with the next part of the talk. It's going to be very short. We don't have much time, and this was really supposed to be about quantum, but let me get into the next piece. Yes, really want to talk about Canada, but to do that, I thought I'd start with the US photonics. We estimate that the US has about 385,000 workers in optics and photonics. And this is the components and the systems. It's really systems where most people are employed. So the component would be an image sensor. The system would be the camera, something like this. A little over 3,000 companies, with a little over a quarter of that in California alone. Something like over a third in the Northeast corridor. That'd be from Maryland up to New Hampshire, and from Boston to Western New York. And then about 1/6 of it is in the Rocky Mountain states, and the rest is kind of spread around. So that gives you a little bit of an idea. Notice the numbers again: 385,000 and 3,300 countries. Now I'm going to go to Canada. it's about a tenth. A rule with Canada, if you don't all know this, is sort of everything is kind of a tenth, except for the landmass, right? So the employment, a little bit less than that, but 26,000. These are your own numbers, by the way, nothing magic on our part. About 410 companies, and those numbers might have changed a little bit since that was published. Almost entirely along the St. Lawrence Seaway, which I think you probably know, but you may or may not have ever thought about it too much. So certainly there's some spread around the rest of the country, but very much concentrated in Ontario and Quebec along that seaway, as is a lot of the population, right? And so that's Canadian Photonics, and I would love to go and talk about that a little bit more with you. I'm familiar with Canadian companies, and that's actually scales pretty well. Interestingly, in Australia, also has a landmass, not too far off that of the United States and Canada, has a population a little bit less than Canada, maybe 2/3 of Canada's, but its industry is much smaller by our estimation. They've just done another estimation of their own. But so Canada's actually scales approximately, I'd say, pretty well. As these things with the US and Europe. So here's the numbers. Again, these are your own numbers. The location quotient is something that I did that indicates its concentration. It's just a way of measuring concentration. But Ontario and Quebec having 86% of the employment, and then another 14% spread around the rest of the country. Okay, now the last part, what's a hot topic? This is one of my favorite topics. And the reason I came up is because we've all been to conferences and your boss paid for you to go and said, so what's hot? And you kind of fumble around a little bit and you say, well, you know, you were interested in this thing and you were interested in that thing and you saw your friend and all this. And maybe you don't have a good answer. And especially somebody like me, I used to work in market research. Now I work for OSA, and I'm covering a lot of different things. And I'm always looking for the things that maybe everybody else is not looking for. And so sometimes what's interesting to me is not what everybody else is interested in. And so I realized that the problem is you come back and you say, well, on the one hand, this, or on the other hand, and that just doesn't look good. That looks like a PhD answer. It's not. Your boss may think twice about sending you on the next trip when we start traveling again. And so I realized that, but it does matter where you're coming from, what your context is. And by that, I mean that, you know, everybody has sort of different frame of mind. Your boss has one, you have a different one. And so if you understand that frame of mind, you can answer that question. So I'm going to give you a few thoughts, and then you can use that yourself. And so next time you see what's a hot topic or you read an article, you can start to put it in context, and you realize a lot of times people mix these things up, by the way. You will see plenty of articles in the trade press where they mix up these hot topics, and maybe it's okay, but you'll start to see them in a different light. So first of all, there's regional language. In North America, we tend to talk about what I call the Apple economy. So these are consumer products, 5G, autonomous vehicles, Internet of Things, AR, VR, AI, cloud, et cetera, et cetera. This is all coming from the private sector. Apple, Microsoft, Amazon, Google, Facebook, but also Alibaba. And it's not just North America, it's also Europe and Asia, but that's very much characteristic of North America. It's not driven by these big government programs. It's currently the Apple economy. Now, elsewhere in the world, you'll see something else. That's also true, what I just said, but if you hear about Industry 4.0, you can imagine, oh, okay, that's often something they talk about in Germany. They talk about smart cities, quantum, certainly. And then there's the whole Brexit, which is a very European phenomenon. It affects all of us. And in China, they have the Belt and Road Project, made in China 2025, 1,000 talents, et cetera. Now, it's not that when you talk to someone in China that you'll immediately hear these terms, but it's in the background. These are big government programs, and that's the top-down policy is very prominent, very important in Europe and China and Asia in general. And so that's one thing, is as you go to different places of the world, what's hot, what's important varies. The next thing is vertical markets. So not everybody listening to this webinar necessarily knows what a vertical market is. So let me just walk through that very quickly. You have these vertical markets. I'm going to name them in a moment. They go from materials to end use. The money comes from at the end user and filters back through the supply chain. The science starts at those enabling disciplines in the universities and then works its way through the chain the other way to the end user. And so let's just put some names on these. We identify 8 that are relevant to optics and photonics. This is communications, displays, machine tools, et cetera, et cetera. You may have your own list. We could also add another one, is those picks and shovels that I mentioned earlier, the scientific market. That's a market in itself. It's not that big, like, you know, making mirrors for telescopes, for big astronomical telescopes and things. But anyway, it is kind of a market by itself. And then you have these enabling disciplines down below: applied optics, spectroscopy. All of these are relevant to optics and photonics. Some maybe more than others, but the that are enabling the new things that are coming along, or improvements in the things that are in those verticals. And then you have these universal drivers. So I have to throw this out right away. You have mobility, automation, and cost. Yeah, these are trends, sure. Mobility almost everywhere. Automation certainly. Smart this, automated that. And cost is not really a trend. It's so universal, so timeless. But I put it out there because if I don't, somebody will say, well, you didn't mention mobility. You didn't mention automation. And so that's, yeah, those are hot topics, definitely, everywhere. Yeah, so if your boss asks, well, you can always pull those out if you're short of ideas. And then, whoops. And then we have, I'm going backwards. Here we go. Now, this starts to get into more detail, and it's kind of busy, so let me just work through. On the top part of these, in these verticals now, is you have these hot driving forces. So on the left-hand side, for example, traffic. Well, COVID drove a lot of traffic, internet traffic up, obviously. 5G's coming, the cloud, that's a trend that drives a lot of what happens further down in the vertical. I mentioned the Apple economy. I mentioned in Industry 4.0, personalized medicine, life sciences. Again, COVID, that would be a new one that just sort of popped up as a very important driving force now for lots of development. And then as you go down, you have these systems that are being developed, LiDAR, for example, or 400G, 600, 800G in communications, AR, VR. And then as you go further down, you have the new components popping up, quantum sensors, perhaps, or materials even, perovskites. If you're working in the solar vertical, then you should be paying attention to perovskites and what it's doing there, because that's a new material that is could potentially change things in solar. And then going all the way down to the enabling disciplines, this would be particularly at the university level, you have quantum photonics, integrated photonics, metamaterials, organics, et cetera, et cetera. And I think we're able to shoehorn most of the academic trends and the government funding trends into these 6, but not necessarily. There's always other ones, and somebody's going to say, well, you didn't list my particular favorite hot topic, and that's fine, but because we only have so much room on the slide. But the idea is that you have these sort of trendy things down below, and what you're basically doing here is you're following the money. If you're looking at the top of the supply chain, then that's the end user money. If you're going down, then it's somebody else's money somewhere in there. At the very bottom, that's the federal spending or provincial spending on research. You're following the money and looking at it that way. That's all I'm going to say about hot topics. I said just a couple words about Canada and your employment, which may be a starting point for discussion. And then I've given you a couple ideas for hot topics. I could go on this, but I think you get the basic idea. Break down the problem into, following the money, or what region are you in, or what vertical are you in, and go from there. And then it starts to become a little bit clearer. And then when you hear other people bringing up hot topics, you can say, oh, well, that doesn't really apply to me because this or that. And you may be already doing some of this because you know your vertical very well. But I think sometimes it can get very confusing when you talk to people or get asked about it. So once again, this is going back to the first part of the talk, this is the roadmap report, the quantum photonics roadmap. Every photon counts. You can download it. Again, is osa.org/OIDA roadmap if you're not an OIDA corporate member. And if you have questions, we're going to have time for questions now. But also, if you think of something later, please contact us. We'd much rather answer your questions, clarify anything that you have, and continue the discussion than for you to go away, maybe not sure, not understanding everything that's in there. So thoskin@osa.org or oida@osa.org. So with that, I'll stop, hand it back to Nicolas, and for questions, discussions, whatever we have time for.
Well,
Thanks.
thank you very much, Tom, for this interesting presentation. I remind everyone that you can ask questions by clicking on the Q&R logo at the bottom of your screen. We already have one popping up. What is the interest of Corning in quantum technology?
Well,
why was Corning involved in this roadmap?
yeah, that's a good question. So I shouldn't speak for Corning actually. But I can say maybe a few things. So I think for the most part, it's trying to be a good citizen. Corning is a large company. It's involved in displays and fiber communications and a number of other, over the years, it's been involved in much more. It's a glass company. It's been around for 150 years. And they've been very involved in OIDA throughout its history, which goes back to 1990, 1991. They've been part of the leadership for many, many years. I think most of it is really just driven by that. They just want to make a contribution. Certainly, there's some topics that they're interested in, but I think they felt like quantum was one that was sort of underserved here, that could receive a lot of clarity. And they had an opportunity to help out and make a difference. And I think that's where it's coming from. But yeah, you'll have to ask Corning perhaps for more details on that.
Yeah, so hopefully Corning is interested in be an active participant in the field and be a user or some pulling force on the market. So, okay, if I go with my own questions, a key takeaway that I believe I took from the presentation is that there's a lot of room for or need even for development of components. So the picks and shovels. So what advice would you give to small and medium companies who have been in the field of photonics and relatively small markets that are looking at this field of quantum photonics? Do you have any advice or enlightenment on what could ease or what would be a way to start a transition towards quantum photonics?
So that's a really good question. So one thing that comes up a lot is there's something like 100 different laser types that have been proposed for these technologies. And in our roundtable discussion last week, there was 10 from AO Sense alone that they use in 2 different wavelengths in 4 different places. And so there's a need to down select on that. There's also a need for fast low loss switches. There's a need for deterministic single photon sources. So some of it is like the lasers, the technology is there, but we just need to advance it. And so good engineering or taking some risk and doing some investment is necessary. In other cases, like the quantum memory, quantum repeaters, the deterministic single photon sources, that just isn't there, right? That just doesn't exist. So there needs to be investment in that. So I think some of it is coming up with a better, just a better product that can be affordable, clever design, and other parts of it does require some science. Not much, actually. I think a lot less than you might think, but again, I mentioned the quantum memories and the quantum repeaters. So if somebody has ideas for making something like that, and there a lot of people working on the science. It's not that nobody's working on it, but somebody will come up with the clever ideas, and hopefully they'll be able to run away, with that market.
And does the roadmap itself? You mentioned a little bit this idea of requirements, of specific requirements of these photonics technology for the quantum information market in general. Is there in the report at least an overview of requirements, of technical requirements?
So there is a lot of technical requirements, and I'm pleased that we were able to do as much as we were, because when I started this, I thought we're not going to be able to do very much. you have to put it in context. I think a lot of times what people do when they think about a roadmap, they think, oh, I know, I've seen the old semiconductor roadmap, ITRS, it was later called, but the semiconductor roadmap from the 90s. And if you've ever seen that, there's exquisite detail for DRAM feature sizes and pin counts and all this kind of stuff, or microprocessors or ASICs. And I don't think there's any roadmap in the world that is at that kind of precision and development. There was so much money that went into that, so much precision, and probably never to be repeated again. So no, we're now nowhere close to anything like that. The fact that we have anything at all is pretty remarkable, I think. But having said that, again, there are these different approaches to, for example, detectors or single photon sources, where we kind of know where the state of the art is. We know we'd like to advance it. The people working on this, for the most part, are saying, well, of course, customers always want better performance, for sure. But for the most part, the parts are there. The huge step is to now do that, but make it cheap and usable in the field. But yeah, while you're at it, make the performance better too. So you will find that information in the document. It will not be to the precision, probably never will be at the precision of the semiconductor roadmap. That is a really unique effort.
So I see in the list of participants, we have a lot of people from the photonics community and a good portion of academic researchers. So would that be one way to, for a researcher in photonics, and again, not really familiar with what quantum photonics entails, I suppose that this report might give at least some direction of where there's a need or a direction to go.
Yeah, what's the purpose of a roadmap, really? It's kind of a way to have a conversation, right? It's a way to focus the community around a conversation, and that then can go somewhere else. So companies, they have smart people, they can go and just do it maybe without the roadmap. But the more that the community has that conversation, the better. Now, maybe sometimes it's not even necessarily what's in the roadmap itself, but all those conversations and workshops and webinars like this one that help get the community aligned and towards that goal. But to the extent that you have actual information in the report that can clarify these things, that's also good. That you can document it, then that's good too. So I see the purpose of any roadmap is really being a catalyst for the general conversation. It's not so much to say, call out specific things, but that too, if for example, the U.S. government, if you have a document that's coming from industry that says, we need more money on this particular thing, quantum memory or something, and that carries a lot of weight, as opposed to, some special interest that comes up and says, well, please fund us, right? If you have the community coming together and coming up with that determination, then that can be very effective.
That's a good point. It's exactly what we're trying to do with this series of seminar, to
Yep.
build a sense of community. And I'm pleased to see that we're beginning to really coalesce people from different backgrounds around the same forum. So that's a very nice rallying point that is starting today. We have a comment and question from Alain Villeneuve. Hello, Alain. So a comment saying it was a great talk and thank you for that. And the question is, sometimes the roadmaps lead to standards. So is there any work being done for defining, what are their standards and for Quantum 2.0, and maybe a sub question, standards relating to the photonics aspect?
So standards always comes up as a question, and it is so early for that. So yes, there are groups that are working on it. So for example, the Quantum Economic Development Consortium that I mentioned earlier, they've had some meetings just even recently, and they talk about it. They are not going to be the standards organization, but they want to be part of that conversation. I think where you can talk about standards at this point is some things like just terminology, or how you measure something, how you measure a qubit, how do you measure how is it like the number of gates and some of these things, like how just basic definitions. Then they can go to, maybe they could start to talk about standards for materials, for the sources of certain materials. If you need, there's a lot of pretty exotic stuff that's needed out there, like diamond. Well, maybe the defect levels in diamond, they can start to talk about standards and measurement metrics for that. So they're at such an early stage that's almost we're not used to thinking of it in that way. And so, and yeah, they will come, but when you have, just like with roadmaps, to have standards, you really have to understand your applications really well. And it's so early that it's very difficult just to even do that. So sure, the standards will have to wait as well.
Okay, thank you. We have a question from an anonymous spectator, but it's also a question that I was certainly going to ask you. So another end result of roadmaps could be to serve as guidance to governments for provincial and federal government. Are there emerging themes, or is there, from your experience, any takeaway that could, you know, some advice that governments could follow to try to spur?
Yeah, one of the things that we tried to highlight was in this roadmap to really take that commercial and industrial point of view. I think there's a lot of attention and that's given to the academic science side, right? It's a really interesting area. There's a process for that in every country. There's an R&D funding process, and so you could add more money to that. But what we really wanted to emphasize was this thing about moving from science to engineering, and that it's not just the quantum physicists, but it's also all these other people that are needed, including your basic, just people with basic STEM skills, without getting into that whole subject of, you know, we need to educate more STEM. We wanted to emphasize those things. So the things that you'll notice in that list, every photon counts, integrated photonics, lower swap, et cetera, they really emphasize a lot that aspect of it. And that's something that I think the governments need to know. I think they appreciate that. They can relate to it a lot. That's not to take away from some of the basic science and so on, but I think that's something that needs to be highlighted. So likewise in Quebec, while you're doing the academic research, which is vitally important, right? Yeah, you have to have that, but you also need to have these other tools in place as well.
So in short, the main message is to have the whole ecosystem. I think
exactly. Yeah.
You talked a little bit at the beginning of your talk about this notion of ecosystem.
You may not be able to have all the little pieces. Canada is a much smaller country. Even the US is having a hard time with its ecosystem. So Toptica is a German company. They have a US office. M Squared is a UK company. Menlo Systems is Europe. And so even the US is looking at this and saying, wow, a lot of the pieces of the ecosystem aren't here. Wow, what can we do about it? So Canada is certainly not going to be able to have it all, but the more that you can have, and also, you know, through trade and so forth, then it's all good.
Yeah, I think it's a very timely question. In the province of Quebec, I may make the comment also that we've seen during the last year or two a lot of commitment from the Quebec government. Ministère Économie Éducation are pushing on several fronts to try to spur something interesting in quantum information in general, and also specifically in quantum photonics. So very timely question. Okay, thank you for that. And a question from Denis Axam. Are there any VCs in the US and that specialize in photonics, particularly in the Boston and Chicago area?
Oh, okay. So my short answer is they don't specialize in photonics that much. But I have to be careful, and I think it would be better for me to defer and say, I'm not sure I can answer that right on the spot. If I leave somebody out, I'll feel really bad. So I think certainly if you go out there, you'll find there are some. Maybe I can carry on that conversation if the person can email me. But I would say for the most part, VCs, they're looking for opportunities. They don't lock themselves into a specific technology platform. That's, you know, one thing. there is this group out of Bordeaux that has hosted for several years. It was, I think, every other year, biannually. They hosted a symposium, sort of an event around funding, and specifically VC funding of photonics. And then they expanded that, so it's not just photonics anymore, but it's meeting in Bordeaux, and I can't think of the name of it now, but I think they're still continuing to host it. So, and there were some VCs that would go there, and they seem to show up every time as well. So they were certainly interested in concentrating in photonics. But yeah, I'm gonna leave somebody out. So my official answer, I guess, is let's check back with me on that.
Check back with the,
Yeah.
with the email. Okay.
Yeah, please.
Message received. Okay, a question from Élie Genois. What do you see as a major milestone in the development of quantum photonics and its impact on the market?
Well, for quantum generally, I mean, the big one in quantum computing, of course, is the fault-tolerant quantum computer. If it was a commercial product, you could go and you know, there was some service income that was, that's quite a ways off. And so you can list the same things in the other two areas. There already are commercial optical clocks. So that's already been achieved, but we would like to see the next one, the gravimeters, or the, you know, something after that that's a little smaller, more portable, more mobile. And in quantum communications, some take up of, say, quantum key distribution or something like that. Now, the question was in quantum photonics, and so I guess you know, a nice breakpoint would be when the income from the actual end use products exceeds these picks and shovels that I showed earlier. Right now, I kind of lumped them all together. You know, maybe some of those were actually going to the end products. And I'm not saying that an end product in a is something in a research lab, but we don't count that. You know, of course, it's going to an end user somehow. But what we mean is that it's going out into the field in some way where there's somebody that's using it that doesn't have a clue what the technology is inside it and is not about to take a screwdriver and do any adjustments. That kind of end product. So maybe when quantum photonics gets to that point, it's going to be a while. But that, you know, that's the ultimate goal, is that you have the end product market is large and hopefully much larger.
Yeah, another way to frame it is we're still looking for the killer app. And
Yeah.
I heard a comment from the Quebec community these last few months that quantum photonics will be successful when there exists a product that uses quantum photonics, but without the word quantum and any branding, but people don't even know that it's there, but it just works. So yeah, that I think would be a very nice milestone. Okay, and I think that we've covered all the questions that have been submitted so far. So that will be pretty much a last chance to ask a question. And we now have been here a little bit more than an hour. We can extend for a few minutes as long as we need. If not, then I don't know if Tom, you have some last words for us.
Well, once again, I think I'm sharing the screen there. So
Yes.
if you do want to send, again, if you want to download the report, it's osa.org/OIDA roadmap if you're not a member, and it's free. And if you have questions for me, thoskin@osa.org or oida@osa.org for any questions about OIDA or OSA in general. So I flipped that up there again, and but I'll stop sharing once more. And merci beaucoup for the opportunity today. There's a lot of fun, actually, and I really appreciate it. And hopefully, I've been up to, let's see, when was the last time that I was in Montreal? It's been quite a few years now, and Quebec. I love the area, so I hope that once this pandemic is over, we can meet again in person. Would love to come up and continue the discussion on hot topics or whatever suits your interests.
For sure, we would have invited you in person another time. And we merci beaucoup for having joined us at least virtually like this. And with that, this concludes our session. Thank you again to Tom for this presentation, and see you all in the next webinars. Thank you.
Thanks a lot. Thanks.